Hello everyone, so welcome back. This is business statistics. So in the previous two sections we talk about some very simple summary statistics and descriptive statistics to describe the data and visualize it. So today we are going to learn something exciting. So we are going to basically learn how to use the probability functions, especially for the normal distributions probability functions and the binomial distributions functions. So just like the previous classes, if you haven't set up your working directory yet, so please do so. So the code is right there. So we will begin with something nice to visualize. So what we want to do in this code today is to first create a normal distributions. So you don't have to actually understand the process of this. It's just basically a way how we can plot the normal distributions with the norm functions. Later we are going to discuss. So first of all, we are going to create a x-axis values. So we have intervals going from -0 to 20, -20 to 20. So we're trying to make a sequence of number here, and the value will increment by 0.1. So we are creating a lot of number here for the x-axis. So let's run this. So if you're confused about how the x actually looks like, you can always print it out. As you can see, it goes from -20, which is the minimum value, all the way up to 20. And every number in this sequence will increment by 0.1. And then what we're going to do is to create the y values. We want to actually create the distribution density values by using the d-norm functions. So the d-norm function basically allow us to create a distribution values at a particular point. So for -20, we are going to assign a values, which is the density values. And the value depends on, of course, the mean and the standard deviation that we define here. So this standard deviation will take a 0 mean, and the standard deviation equals to 5. So let's run this. And now a y value is being created. Again, you can actually try to print it out and see what it looks like. So these numbers may not be any intuitive to you, right? Maybe you are worried about, I don't understand what this number actually means now. Don't worry, we're going to see it in just a few seconds. Because the next thing we want to do is to plot the y and x. So we have the y-axis, which is the interval from -20 to 20. And we have the y value, which is the density of the distribution functions. And we are going to give a title to this graph and label the x-axis, the y-axis, and then also define the type of class, which is a line graph. So let's run this and see what we return. So as you can see, we are plotting a histogram graph right here, right? So you see this interval, right, of the histogram. And you can see from -20 to 20, there's 19.9, there's a little small tiny interval, and it actually rises up to a certain density value. Well, everything is going to central to 0 because we define our distribution to have a 0 mean, and one standard deviation away from the center is going to take a value of 5, which is around this point. So every value on the y-axis basically pointing at the values, let's say 0, and give you the density, the probability density of that value, x equal to 0. So this is something that we learn in the class when we talk about the normal distributions, right? So usually you will see the bell shape and central at the mean of the distributions, and then what the spread of the distribution will be described by the standard deviations. Well, another way to do this, well, you can actually try to build your own standard normal distributions. So this one is called the regular, right? The X-score regular normal distribution, because it's not standardized yet. But we learned that we can actually have a standardized distribution with a z-score, where the central point, the middle point, is going to be centered at 0, and the standard deviation will be away from the center point by 1 standard deviation. So let's try that. So I'm going to create a new sequence here, C, which is our x-axis value. It will go from -4 to 4, and it has a length of 1000. That means I'm creating 1000 intervals between -4 to 4. And I'm going to basically use exactly the same function, the norm function, but this time I'm actually not defining the mean and the standard deviation in this function. The reason is because the denorm function actually has a preset default value for mean and standard deviations. As you can see, it's always going to give you a 0 and 1 for mean and standard deviations by default. So that's exactly what we want. So let me run this too. And I would like to plot this graph just like the previous. So we want to actually pass in the x value on the x-axis, and we want to define the density values on the y-axis. And we give a name, standard normal distributions. This time the x-axis is going to represent the z-score, right, the z statistics. And I'm going to give some additional color to it. So let's print this plot right here. Oopsie. So I guess something wrong with this. Let me just do this one more time. So I have the C and D. And let's just run this. Oh, I can see what I did wrong. I have the x stuck here, so I'm supposed to use C, right? So every value from my x-axis and plot it to a y-axis. And I'm going to run this plot again. And now you can see how I have a nice standard normal distribution with a z-score, which is a standardized score at the x-axis, central in the 0 mean, and 1 standard deviation is exactly 1 unit away from the central point. Well, we can actually try to give some flavor to it. For example, we can plot lines to basically indicate the shape of the curve. But again, we are just trying to visualize at this point, and we're not doing any analysis here. Well, one last plot that I want to show you with the normal distributions is you can also use the our norm functions. The our norm function actually return a total number of sample you requested that is going to distribute just like how you define in these functions. Again, the our norm function actually has a default mean of 0 and standard deviations of 1. So I'm going to create 1000 number in this case. I'm not creating a y value here, but I'm actually creating a samples here. So I'm creating 1000 observations randomly, and this sample will have a value central at 0, mean, and also a standard deviations of 1. So let me run this function here. So you can check to see if those numbers, right, the random sample I just created, it has a 0 mean or standard deviations of 1. So let me run the mean function here. So very close, right? So again, it's a random sample. It's not exactly standing at 0. That's exactly what I want. And the standard deviation should be very close to 1. And there you go. So this is a good way to actually create a simulated data, right? So you can simulate a data set by using our norm functions if you want to create your own normal distributed samples. Well, but again, our goal is basically plots, right? So we want to plot this data point out on a histogram. So let me run this. And now you can see the frequency here, right? From 0 to negative 0.5, I have the frequency count of the number at that point, right? Above 150 counts. Most of them are actually centralized in this area, negative 1 to 1, which is okay because it's a random selected sample. So we don't expect this to mimic exactly the normal distribution, but it should be very close, which exactly the shape that we want. Alright, so now we have some idea about the visualization. Of course, we just want to see it first, and then we want to apply those norm functions that we are going to talk about in just a second. So when we actually having a normal distribution functions, for example, a function like this, we are always asking the questions, what if we are standing at a standard deviations of 1 or negative 1? What is the probability maybe on the left tail, or maybe the probability on the right tail, or maybe some number in between the standard deviations, or maybe the two tails outside of the central area? The reason is because this area, the area in this distribution actually always add up to 100%. So if you know that you are going to have a score of negative 1, and you want to ask the questions, well, what is the probability to actually randomly select a number that is less than or equals to negative 1? We are basically looking at the probability on the left hand side of this tails right here. So again, well, how do we calculate? Well, the way how we do this is very easy because we have a p-norm function here that help us to figure out the probability. For instance, we are given an example here. We are asking a question, what is the probability for randomly selecting a sample where the sample will have a score of 27.4 or less? Given the fact that this little samples, right, that we are going to draw, or this sample size of I don't know, some numbers, right? Some random numbers that we're going to draw has a mean value of 50 and a standard deviations of 20. So all we need to do to figure out the probability here is to use the p-norm functions. So again, the p-norm function also has a default of 0 mean and standard deviations of 1. But you can define your own. In this case, we have a sample that has a mean equals to 50. And the standard deviation equals 20. So we want to know what is the probability to choose a random number that is falling below 27.4. So all you need to define is the score that is going to sit on your distributions, the locations, right? And then you define the mean, the central point of the distributions, and then you define the spread of the distributions. So let's run this and interpret the results. As you can see, I get a result right here. So 0.1292. So that means on the left hand tail of this distributions, where the distribution has a mean of 50 and standard deviations of 20, if I'm going to select a random number that is less than or equals to 27.4, the probability to do that, or the area on the left hand side of the tail, is going to add up to be 12.92%. So 12.92% of the chance that we are going to get a number that is less than or equals to 27.4. Well, what about if we don't want to get a left tail probability? What about we want to actually calculate something on the right hand side, right? So to do that, it's pretty simple. The logic should actually follow. So let's suppose I am interested to calculate something here. So suppose we have a weight produced at ACME weight worked, right? We want to basically find out there is a selected samples, right, in this work, and the sample actually has a mean value of 17.46, and the variance of the sample is 375.67. And we want to actually find out the probability in this case, right? So the probability to randomly select a widget that weighs more than 19 grams. So in this case, we are basically asking a question. We have a subset of samples, and we want to actually find a random number from this one sample that we select from this productions that is going to have a weight more than 19 grams, right? What's the probability? Well, as you can see, the mean of the whole sample production is 17.46. 19 gram, it's above, right? So it's basically pointing at the right-hand tail of the distributions. So to do that, it's not too bad, because all we need to do is to figure out the probability on the left-hand side of the tail, and then we are going to use, the left-hand side of the tail, right? And then we use 100%, which is 1, minus the left-hand side of the tail, and then we will get the probability on the right-hand side of the tail. So in this case, well, let me run these functions here. So this sample has a mean of 17.64, and since this is not a population data, remember in the class we talked about when we're dealing with the sample data, we have to define our standard error, and the standard error or the standard deviation for the sample distribution is going to be a square root of the n values, which is our standard deviations. This is standard deviations, but the square root of the variance, right? So not regard the sample size here, but because we're given the information of variance instead of standard deviations, right? Alright, so we take a square root of the variance and we get the standard deviations. And we're going to use 1 minus the probability on the left hand side. So let's see what we get. Alright, so we get 47.20%. Right, so the left hand probability here is going to tell you we have 47% or 47.2% of a chance that we are going to select a random sample that has a weight 19 gram or above. So those are very, very useful functions that we can use to calculate our results, especially if our interest is to find the probability within a range of the intervals. Well, now we have other norm functions that we can discuss here. Well, another norm function is called the Q norm functions. So the Q norm function basically is the reverse of the P norm functions. So what does it mean? So the Q norm function actually calculates and returns the inverse of the cumulative distribution frequency of normal distributions. So what it means is basically you're given a percentage of the distribution you want to calculate, right? You want to see, and this Q norm function is going to return the positions, the x values for that particular percentile range, right? Or that percentile locations in your distributions. So for instance, we want to find out, well, what is the 80 percentile in the normal distributions with mean 10 and standard deviation 1.75. So what we mean is we want to know by adding all this distribution probability from the left hand side all the way up to the higher end, I want to have a probability of 80% of the distributions. And what is the score on the x-axis that it's pointing at that particular percentiles in our data? So to do that, very simple. First, you define what is the percentile, right? right? You want to actually locate, so in this case 80 percentile. The mean of the distribution is 10, standard deviation of the distribution is 1.75. And you run this, and it will return. So we have the mean of the distribution is pointing at 10. The 80 percentiles, right, cover 80% of the total sample in this study, basically has a value of 11.47 or lower, right? Anything equal to this value or lower than this value add up will have 80% of a chance to happen. And that's basically what the 80 percentile means, right? This number is standing at the 80 percentiles in the distributions. Well, another applications, right, for this Q norm. Let's say we want to find out there is a normal distribution with a mean score of 100 and standard deviations of 15 for IQ score. We want to find the persons, or maybe the score, the IQ score that puts you on the 95th percentile in the distribution. That means you are, if you get this score, you are basically the top 95, right, among these samples. So again, same thing. You put the percentile number, 0.95. You define the mean of the distributions, which is 100, and the standard deviations of the distribution, which is 15. You run, and it will return. If you have an IQ score 124.67, well, you are going to be the 95 percentile in this samples, or you are the top 5% highest IQ in these samples. So the Q norm function is actually very useful when you need to actually reverse to get the X scores in your problems, right? When you know what locations you or what percentile you are trying to figure out the locations, you can simply just put it out and define the mean and standard deviations, and it will return the result of X to you very quickly. Well, the last two norm functions here are the two that we just saw in visualizations. I think those two are not very frequently used, especially in your assignment problem. What it usually apply for the R norm function and the D norm function is to use for visualizations when we try to plot it. So for example, the R norm functions we talk about, it generates number, right? We define the number of samples, observations with a given mean and standard deviations. So this will automatically randomly generate some number in R so that it follows the mean of 100 and standard deviation of 15. Well, on the other hand, you can actually run this, right, very quickly and see the results. Right? You can actually print the X right here in the histogram, and you can see how the sample is being created, where some of the data is actually here in this range, some of the data is in this range, some extreme outlier will be on the side of the two tails. And the D norm function, on the other hand, gives you the density value, right? You give the D norm function a number, it will return to you a value based on the mean and the standard deviation you defined. So let's suppose we are using exactly the X random simulated data here, 1000 data here that we simulate. And I'm going to basically define the X value on the graph, and I'm going to define a Y values using the D norm functions. So I'm basically mapping every single data in this random sample here. And I'm going to run this, and I would like to actually plot this, right, in a line graph. So I'm going to basically run the last two lines right here. And you can see how I can actually plot this very nice little curve right here. This is basically the density values at every single score that I define on the x-axis. So you can see how we can use the dnorm function and our norm function to do visualizations for the distribution. But again, that's not our main focus in this class. So I'm just going to basically show you a few examples here, and we just wave hand on it. Well, the next thing we want to talk about is the binomial. So the binomial distribution is the one that's handled the discrete choice, especially for a case of success and failure. So again, a little background of the binomial distributions. We are trying to measure the number of success and failure in a particular trials, and we are basically using the probability of success and probability of fail to map our distributions. So again, just like the previous, I would like to plot a binomial distributions with a given x-axis value here from 0 to 50 incremented by 1. So once I have the x values, I would like to actually create a binomial distributions here by defining the density values, right? So the d binom basically define the density values of every x that we just created here. And this binomial distribution would take a mean, it's going to take a sample of 50 trials, and then the success of this trials will be 50%. So 50% of a chance will success, 50% of the chance will fail. So let's run this, and I'm going to plot the x and y value here again, and I'm going to define this as a binomial distribution with a p, or percentage of success, right? P basically define the proportion of success as 0.5. So the x-axis is number of success, density is the density value. We are using a histogram light graph, and then some color edits. So you can see most of the trials in this random sample will have a success rate stand in the middle of this distribution. So most of the time, when you do 25 times, usually it will give you a success, right? So success case is standing in the middle. When you're doing a 50-time trials, most of the time you will get a success in the middle, which is the 25 times. So again, you might actually ask, well, why is it 25? Because 50% of a chance, right? You pay 50 times. 50% of a chance you are going to success in this trial. So that means, well, 25 of them are going to success, right? So that's why you see the spike right here is centralized at 50. However, you can play around with this number and just map this binomial distributions for yourself. Let's say I don't like the chance to success is 0.5. Let's say the chance of success is going to be much lower. Let's suppose the chance of success is only 10%. Let me run this y value again, and I'm going to plot this functions one more time. Now, can you see? If I have a success rate equals to just 10%, 0.1, we do 50 trials, well, we most likely will have 10, or in this case actually 5 of them will be success in our trials, right? So you can see this number of success will be standing at the value of 5. And again, why? Because every 50 times of trial we do, we expect to have 10% of a success case, so that means will be 5 cases will be success. So you see this number of success will spike out in this range right here of 5. So something to keep in mind, you can actually imagine how we define the binomial distributions and how the percentage of success, right, will make a difference of the shape. Well, the graph only give you a good idea of how the shape of the distribution. Let me just change that back again. And there are some functions in R that actually help us to plot the distributions in different ways. So I guess I have another example right here, right? So it's the 20% case. You can actually try it out yourself. There's an 80% case. You can see the screwed of the graph to the left-hand side on this case. So you can actually play around with this plot. Those are not the main subject to study in this lab hour. The thing is, well, we want to actually create some random samples. Just like the previous case, right? We want to have some random sample that follow the normal distributions. And now we want to generate some some random sample or simulate some data set that follow a binomial distribution. So what does it mean? So we can use this our binomial functions to create simulates, right? To have some random simulates data. We want to create one, in this case, 10,000 data points that follow a not binomial distributions for 10 trials each time and 0.5 of success rate. So I'm going to create this. And again, if you wonder what the Z looks like, you can always print it out like this. So as you can see, I have 1,000 observations here. The first observation basically tells us for every 10 trial, I do 10 trials in this study, and I got 7 success in the first time. On the second time, I do another 10 trials. I got 7 success case also. The third time I play, I got 5 times success, and the fourth time 2 success, and so on. So we are basically creating a new simulated data sets here so that we can use for plotting. Again, what we are trying to do is to use the histogram. So we plot the histogram with the Z value, right, the random number of success, and we call this a binomial frequency distributions. And let's see how it looks like. Okay, so we have a result here. So you see the histogram that is giving you the idea. Most of the time we will success at this point right here, which is 5 times that we play the trials, right? We do 10 times of trial. Most of the time we get 5 times success. We get some are at the 4 trials and some are at the 6 trials. 6 success and 4 success in 10 trials. Very rarely you will see doing 10 trials you will get 10 success, or 10 trials 0 success. So again, well, showing you the graph helps you to visualize and understand the distribution shapes and how it affects the probability calculations. Now what we want to do is to apply the binomial functions in R. So similar to the previous study, the normal distribution has the P, D, Q, and R functions. Same here, the binomial distribution function also provides you with the P, D, Q, and R function, and they are exactly the same meaning. But let's see the applications of them. Let's suppose I want to actually understand. We have a distribution that we define here, the binomial distributions for 100 trials, and every 100 trial we get 25% of success rate. Here we defined the binomial distribution with a size of 100 and probability of 0.25. And I want to know what is the probability, right, that we only success exactly 27 times. Now the good thing about the discrete distributions or normal binomial distributions, actually not a good thing, but it's just like one unique feature, is that you can ask a particular questions like this. Well, I want to know just 27 times of success. You don't need to worry about an interval like from 27 to the lowest number, or maybe 30 success case or more, because you can literally ask a particular value at a particular point for a binomial distributions. So the D binomial function is going to give you that probability at that particular point in the distributions. So how likely I will get exactly 27 times of success? Well, let's run it. So the probability is 0.0806. So that means approximately 8.1% of a chance that you will get exactly 27. Nothing more, nothing less. Well, let's see the applications of this d binomial functions. So suppose we are doing exactly the same study here, right? We actually have a probability for finding something defect in the productions, which is 0.5% of a chance. And suppose we shipped in carton contain 25 widgets. So one carton contain 25 widgets. So what is the probability that we randomly choosing some of these widgets that's going to be a defecto, and we only find one of them? So the question we're asking is, what is the probability where the number of the success, well, in this case we find the defect is a success, right? That is exactly equals to 1. Well, given the binomial distribution we just described, we are going to do a 25 times trials because every carton has 25 units in there. We open a box. Well, every time we open a box, there is a 0.5% of a chance there is a defect product in the cartons. So again, well, I'm going to basically define this binomial functions. One successful defect case size is 25 because every carton has 25 units. The probability to find a defect is 0.005. So what is the chance to find exactly 1? So the chance to find exactly 1 defect in one box is approximately 11.1%. So this is basically a very, very important and very useful binomial function that you want to use to figure out a probability problems. Well, the p binomial functions work almost the same way as the p normal distribution, right? P norm functions. The p binomial functions basically give you the capability to ask the questions: what is the probability for x is equal to some value or below? Right? So we're basically looking at the probability on the left-hand tail of the distributions. So let's suppose we're giving a binomial distributions has a mean value of has a number of trial 100s, and the probability for success is 0.25. I want to know what is the probability where we can find at least 27 success case out of 100 trials. At least, right? So 26 total okay. Right, so that means we are looking at anything equals to 27 or below 27. So let's run these functions. Oops, maybe a misspelling right here. Yes. Okay, let's run that. Okay, so the probability for picking 27 success case or less will be 72.73% or 72.74% of a chance. So you can actually imagine why, because for a trial of 100, there's a 25% successful rate. So that means on average we should pick 25 units that is success, right? Most likely happen there. Anything that go from 27 or below, 25 it's also include. So that means, well, most of the cases that you find in these trials, right, of 100s will definitely be anything around 25, or you are including less than, then it will keep accumulating, adding more probability into it, and that add up to be 72.73% of a chance. So you can play around with this probability functions with like an actual example. So for the same setup right here, right, we are basically examining, opening a box of 25 widgets with a probability of 0.005, a probability to find a defect. What is the probability to choose a carton that has no more than one defect widget? Right, so no more than one, that means, well, one is not even included, right? Or in this case, well, no more than one, you can include one, right, but just nothing more. So in this case, we are using the exact same setup as previous. Can you see the setup right here in the functions? Well, the question here actually answer equals 1, exactly 1. So here, we also include 0, right? 0 is actually less than 1. So 1 or less. So what is the probability to find 1 unit of defect or 0 units of defect when we are inspecting 25 units in a cartons? So let's see what's the probability here. So in this case, we actually has a probability of it's giving you the right hand tail probability here. So this probability, it's basically anything include 0 and 1 right here, right? So this side will give you a probability of 99.3% to have at least one or none defect in the carton box. So you can actually imagine why, because, well, the probability to find one defect in the box is 0.005. So it's very, very small, extremely small. So you are basically including a probability for not finding it. Then obviously the probability is going to be extremely high too. Alright, so the last equations we want to demonstrate here, which is the Q binomial functions. The Q binomial function is the reverse of the P binomial functions. So you're given the probability that you want to search in your distributions, and the Q binomial function is going to return you the locations on the x-axis. So for example, we have a binomial distributions with trial of 10 cases, and number of percentage of success is 25%. And I want to know the 10% distributions, right, in the graph. So basically, we are asking the 10 quantiles, right, or percentile. In the previous case, this time it's a quantile. So the 10th quantiles in the data, right? So that gives me 10% of a chance for anything of that positions and below. So let's run that, and that gives me a number. So this number is a 0.056. So for 10 trials, we have a 10 quantiles of these distributions pointing at the locations of 0.05. So that means, well, less than one time that could success, right? Given the 0.25% of successful rate. So this is locations, right? Remember, this is locations of your distributions. So in this case, it's somewhere very far from the mean values, because the mean value will be 10 times 25%. That means, well, it's going to be central at around 4, right? I mean 2.5. So 2.5 is the middle point, or the mean of the distributions. And this 0.056, it's very, very far to the left-hand side of that central point, which makes sense because 10% has a very, very small probability. So the left-hand tail only have 10% of a density. That means, well, the number should be very, very far from the mean values on the left-hand side. So again, well, the Q binomial function returns a locations. The P binomial returns you the probability of the tail, and the D binomial returns you with the probability of a single specific histograms in your or bar charts in your bar in your distributions, right? It's just one particular value. Alright, so I hope by going through this code right here, you'll be able to use those probability functions and trying to answer the questions in the assignments. So if you have any questions, so feel free to contact me. Alright, so I will see you guys next time.